So we were discussing the current source up here in the last video, and we'll now move on to do a few other little bits and pieces and also talk about the differential stage. So I just do a bit of cleaning up. I'll clean up in my power supplies, try and make them look a bit nicer. Fine, maybe bring that in a bit, it's a little bit ridiculously large. And I'll pull this down a bit and pull this source down a bit. This is our driving source. Maybe pull that out, delete that. And I might try and make the feedback look a bit neater. Maybe even rotate this one. There we go. Maybe pull these two down as well. We're probably going to end up changing that. So this current source, very similar to this one, only a slightly simpler design. So we'll just make the necessary changes. We just make the models a bit better. So we can expect a reasonable simulation. And I might make this 2K2 as well. Fine. R7's different value to R3, so let's have slightly larger current. In fact, I should be expecting about 10 milliamps out of here. So when I do my simulations, I might want to go back and look at the power dissipation in this device. It's not 45 milliwatts, that's from previous simulation. Although it may well be accurate. But hello, what's it sad about? No AC stimulus found. Well, that's too bad. It's because I deleted the source I had up here when I was testing that stage, so we can just put 1, 0 there. I don't actually want AC simulation though. I want the operating point. So they've got my dot back here, and the AC has got the semicolon. We run it up. Power dissipation, 152 milliwatt. Well, we'll see. I don't know if the rest of the circuit is working or not yet, but that's quite a lot. It's going to get hot. We need to make some of these transistors a little bit more realistic as well, so we'll make these 753s. And I'll delete that one. Just copy this one across. Control E will flip it for me. And this one I'll make a 653. This one I'll make MJE340. The reason for that is probably in power dissipation. But before we can get accurate power dissipation here, oh, I hate it when they're upside down. Hang on. Let's just make it the right way up. It just looks ugly otherwise. That's better. Might put a little resistor in there, I'll tell you why in a bit. So even in the back of my head, I'm doing things to the circuit which I'm not doing right now, because if I do it all at once, there's no chance to explain. But it's not a process that I have to think about very much. Sometimes you have to think, obviously, very carefully, otherwise you just screw things up. But it's a lot like driving. After a while, you just do it without thinking. You can have a chat with the person sat next to you, or in the back, or you can shout at the radio if you don't like what they're saying. And it's also a little bit like playing sports. When you're playing, especially a fast sport like badminton, you don't think about the next move. Or if you do, it's a very, very quick thought, and it just comes to you and then it happens. You don't plan it like you plan moves in chess. And I suspect the very good chess players also have an element of instinct where they just know, because in their mind they're 5 or 6 moves ahead at least. and they're planning all the possible moves their opponent is likely to make, and they're planning all their counter moves, and it's all mapped out for them. And they don't have to sit there and write it all out. It just happens, almost as if it's on automatic. It's the same with anything you practice a lot, and it's how it is for circuit designers if they've had plenty of practice. So we'll deal with this stage now. When I'm trying to get something to work in the simulator and it's not working, I usually try and simplify it as far as I can. It might even have been well to have just got rid of this for a bit and put a current source there. You could, if you wanted to, just have done that, and that's your current source. It takes all that away. You can set the current by putting the number in. By the way, if you do that, there's a little button you want to press. Right click, advanced. This is an active load. You probably want to push that to explain to Spice that it changes the way it does the simulation a little bit, makes it more likely to converge, which is good because then it will solve. If it doesn't converge, then it can't solve. So I don't really want to get into why R2 and R1 are there. We might do it eventually, we might not. If I wanted to get this stage to work, I know this stage isn't very happy because my output offset is 200 millivolts. Now I haven't done anything with these transistors yet, I haven't adjusted that lot, but I'm pretty sure that if I've got output offset problems, these transistors, okay, they're not good models, but they're not utterly useless. I know this source probably works okay. If I look at the current there, it's 11 milliamps. I said it'd be about 10. Fine. This voltage 1.1. This voltage 200. So there's about a volt across there. Probably explains why this current's a bit small. It's quite large actually, 30 milliamps. But this transistor is on a bit. And I said this transistor, I mean Q12. But the current in R13 is very small, nanoamps, so this transistor is totally off. So we've got problems here. We could, if we wanted to, make these components have the right sort of model. Now, we could try MJ15003. That's quite a meaty transistor, but for the sort of thing we want to do here, we're at 15 volt supplies, we're not going to be delivering a lot of power. We might go for something a bit older, like the TIP 3055, one of the very oldest match pair transistors, NPN and PNP, with nearly the same parameters. This is a good power transistor. You would, well, I say it's not a good power transistor. It's got a lot of things that I don't recommend. It's got quite a low transition frequency. It's not very good for high frequency work. It can't really dissipate a lot of power. It takes a lot of usually it takes quite a bit of current to drive it, because its beta's not very good. It's fairly miserable in most respects, but you could say it's got a low FT. It's quite unlikely to oscillate at high frequencies when we don't want it to, then, because it won't have any power gain at those frequencies. So it depends how you view these things. It's perfectly acceptable for this sort of situation, even though it's probably been around for about 40 years. These are quite big. They're quite big because we really only want them to pass a large current through here, and we get a voltage drop here which acts to switch off this transistor a little bit, just in case the situation arises. This transistor got very hot. You've got a VBE here. IC will increase because the transistor is hot, which makes the transistor hotter. So for a given VBE, because it's got hotter, the IC will go up a bit, which makes it even hotter still. And of course eventually it will blow up. What we really want is to have some bias across here, between this line and that line. The current flows. If the transistor gets hot, the current gets a bit bigger. Voltage across here gets a bit bigger. Since this plus that plus that plus that are all fixed at 2 diode drops, if this takes a bigger share of the voltage, this should get a bit smaller, switch off this transistor a bit, lower the IC a little bit, and maintain the set of quiescent conditions in the output stage that we like. Doesn't actually have to be an ohm to do that though. And you say, oh, it's 29 milliamps in it, the power is 867 microwatts, why are we panicking? Later on, currents will be different. I should say an ohm is as big as I would ever go. Maybe 0.22 would be a pretty good choice. You could even go a bit less if it's going to have very large biasing. Also, we need to do a little bit of tidying here. That needs to come back a bit. That needs to come back a bit. That goes up there. That goes just there. That goes down there. That goes down there. We can also move this one over. There we go. This is our speaker. Oh yes, okay. Unrelated. Maybe I can even move the transient simulation up here as well. Haven't done any transient simulation yet, but we will. So we've got reasonable models for need models for this. Reasonable models for most things except this pesky current source down here. Current mirror. Output offset 13 volts now. Even worse. Now most of this stuff's probably okay. I might be inclined to change this, but we could leave it. Let's see, what's this voltage at? Minus 13, this is at minus 14. So this voltage at minus 14. When this is at minus 14, what it means is this transistor is turned on a lot. It's turned on a lot probably because this voltage is a bit high. 13.47, 15. .5. So that's 0.765 per transistor if they're biased the same, which they're not, but let's just pretend. 0.7 something's a lot for a transistor. Conduction will start at about 450 millivolts. By about 650 millivolts it's good and turned on, and by 0.7 it's well into turned on hard, and by 0.8 or 0.9 it's blown up. So because the current flowing is so enormous, if there's nothing to stop it, or in this case it's switched on and it's taking 26 milliamps, but from this source only 11, so the rest probably from here, right? 15 plus 11 is 26, 26 in there, yeah, fits. This one, nothing doing, switched off, no surprise. This one's turned on, yanking this voltage down to the ground, down to the minus rail. So that's the situation we find ourselves in. These transistors are turned on too much because this fancy current mirror is not doing its job properly. If we put some decent models in, I hate that word, especially if I see it written down, some better models in. Let's put in some 653s. I tell you, I would delete these because they're all going to be 653. Ooh, that's different. We can run it again, see how we get on. Things have improved. Still 2 volt offset, that's very, very large. 110, 400, dear. Yes, right. So this node is at -3. There's a couple of things we still need to do. This, I don't trust it. What's this current? 3.06, this one. 3. Okay, fine. It's not a sinner, but there's balance here, which is what we should have, because this business, the current mirror, and these two try to balance the currents in the two collectors. I'm still a bit worried this node is too high in voltage though. Turning this on a bit too much. I have to come up with a plan there. It may also be that the biasing is ineffectual in the output stage, and it may also be that the feedback resistances are too small. So we would change the feedback resistance. The other thing it might be is that the base current leaving Q5 flows through R10 and into effectively the ground, because this is only 8 ohms. Although this is 10, which is probably what's really involved at the minute. And there's 50 ohms here. Now the current that leaves here sees this voltage, and because the base current leaves the 753, the PMP, it will set up a voltage across here, and the source, I can imagine, is switch off at the moment. So 50 ohms to ground. This one sees 10 ohms to ground and whatever funny parallel we've got up here. 490 plus 8, more or less. So we might need to deal with that first. Then we'll see if this is at fault. And if it's not, we'll consider this again. And if this voltage is held too high by these transistors. And if it's not this, we'll go and inspect that, and we'll keep going until we figure it out. The problem sometimes you find with the circuits with a global feedback loop around several stages is things that look bad over here can be due to this or this or this or that, or who knows, and it's very difficult to pin down what's actually at fault. Takes a bit of experience. So we want the resistance looking out of this base and the resistance looking out of that base to be the same. So the base current that flows jacks the base off the zero by the same amount on either side, so you get the same VBE change due to the base current flowing through these resistances, and that means you don't get any imbalance due to the base resistance looking out being different. But we do want some gain, and it looks like the person wants the gain to be 1 plus that over that, which is 4.9, 5.96 effectively. So what we could do is make these values considerably larger. The other thing we need to do is to try to make the amplifier have no gain at DC, or unity gain at DC. The reason we want to do that is we don't want to amplify the DC offset that we get from this stage. Offset is responsible from this stage. This stage is responsible for the offset. If we don't want to amplify the DC, we need to put some capacitor here. The reason that works nicely is effectively we have an op-amp where we've got, let's pick an op-amp out. This will be my op-amp. We've got, hang on, let me turn it upside down. I'll not power it up because there's no need for the demonstration, but I'm going to put together this circuit. So this is effectively my V plus, which is here. This is my V minus, which is here. R11 is R10, R5 is R9, C6 is C5. If I get rid of that and run that straight to ground and ask you for the gain, you'll say, 1 plus R11 over R5. Great, 1 plus R10 over R9. Fine. If I say, okay, I want to make a high pass filter, you'll say, alright, well, we can do that. And then what happens? Well, as frequency increases, we will end up in a situation where the gain is adjusted because the impedance of the capacitor is changing. As the frequency increases, the impedance of the capacitance drops, and we end up in a situation where you've got 1 plus R11 over R5. But at low frequencies, where the impedance of the capacitor is not negligible, it has some impedance. We'll have a impedance here of 1 over 2 pi f times C6 plus R5 because they're in series. In other words, this bit will get bigger by the amount of XC6, where XC6 is the impedance of C6 at that particular frequency, 1 over 2 pi f C6. What does that mean? Well, it's 1 plus R11 over R5 plus XC6. So you got, let me write that out. 1, no, that's a plus, let's try again. 1 plus R11 over R5 plus XC6, I'll put the brackets in. Now then, if this is getting bigger, it means the whole denominator is getting bigger. And that means that all this fraction will be getting smaller. So the gain is getting closer and closer to 1. XC6 is much, much bigger than, or R5 plus XC6 is much, much bigger than R11, all the stuff in brackets will become much, much less than 1, and your gain will drop to 1 plus a tiny thing, or roughly 1. Now that doesn't move it. What deletes it? F5 deletes it. There we go. Right, so that's what's happening there, and this is our model for the amplifier. All of the other transistors and stuff and things are all living inside here. Bye bye. Right, so I'm going to make these a bit bigger. The value of that we'll come back to at some point in the future. So should we do 49k and 1k? Sorry, 10k. And then we can do, now as far as DC is concerned, this pathway is now infinite impedance, and only the DC can flow through the 49k and into the ohms and down. So I'll make this one 49k as well. The fact that 49k doesn't exist is a bit of a problem, but we'll return to that at some point. I could use 47k and 8k2 or something like that, or maybe even use a couple of resistors to make it dead right. So if we run it now, we'll see what happens to our output offset. Hopefully it will be reduced. Nope, it's increased. Well, there you go. Just shows you, doesn't it? So what's happened? Well, this current is balanced, this current is balanced, with that one there equal. This current, 77 micro, that current, 13 micro. Right. Okay. This transistor, 75 milliamps, this transistor, 400 milliamps. The higher you make these resistors, why is that called 50? Let's call it Rin, shall we? It's not the input resistance, actually, let's not do that. We'll call it something insignificant like R99. I don't want you thinking it's the input resistance. It's not. Could be that I've made these a little bit big, and this current has to produce a big voltage across here, and that's pushing the offset. But I suspect it's got more to do with our dodgy biasing schema. So we can try to adjust our biasing arrangement. First thing I'll do is just delete the feedback line because it's in the way. Then I'll try and make the output stage look a bit neater. Maybe we can try to pull this one down a bit. No, that didn't go well, did it? There we go, try that. Move this one down, no. Move that one down. Get rid of that. Pull this slot down a bit. Move that down. Come here, you. Move that down. We can probably pull this in. Pull this in. Pull this in. Oh, I noticed another problem as well. Just noticed another problem. We might even have to deal with that before we deal with the biasing, actually. Silly, really, because I mentioned it earlier and it didn't ring the right bell in my head to make me think I've got to do something about it. Just pull these back. Oops. Oh dear. Pull these back a bit. Pull that lot back a bit. There we go. You probably move that to there and pull this lot back too. Try and make the diagram a little bit neater. There we go, that's a bit better. Maybe even pull these in. Pull that in. Pull that in. Pull that in. Move those two down a bit. Yes. Why not? Spacebar to zoom to the extents of the screen. Right, so I changed these to this tip 3055 and the tip 2955, and I said that there was quite a low beta, and if we were to look at the output resistance of this current source, well, it's not going to be dissimilar to the output resistance of this current source in terms of order of magnitude. It's going to be hundreds of kiloohms. So it's going to be very difficult for us to drive a signal into Q12 which will provide enough base current to actually turn on the device properly. we probably need to have some pre-driver. So I'll probably end this video here, and we'll deal with the output stage modifications and the biasing if we have to in the next video. Then we'll hook the feedback up and see if we can get the whole thing to go. Once we've done that, we'll have a bit of a talk about some of the things that I didn't pick up on as I went along, and we still haven't talked about the compensation either, so plenty of things still to do, but it's looking a lot more promising than it was before.